This problem, we're going to go over problem number 26. So it states the 12 nanocoulomb charge is located at the origin. What are the electric field at the position? 5 centimeters, 0 centimeters, negative 5 centimeters, 5 centimeters, and negative 5 and 5 centimeters. Write each electric field in the component form. The first thing we want to do, we want to draw a graph here. In this case, I already drew my graph. And so we're going to have point A, point B, and point C. And they're going to indicate it at the positions that is given here. So it's 5 centimeters, 0, negative 5 centimeters, and then plot C, which is 5, negative 5, 5. And so the next thing we also do, we also want to label our coordinate system. So I label my coordinates X and Y here. Also, I'll label my components as I and J. And so we want to look for our given value. So we're given 12 Newton Coulomb charge, positive. So we know that it's at the origin, so we could place it here. And then we're also given different coordinate system where charges probes of A and B and C. And we're also given a constant as well. And so since we're getting our constant values, the thing also, since they're probes, they're going to be repelling. So we're going to calculate the electric field force from here, and then from this also, and then from the top portion as well. And so since they are same charges, they repel. And so the first thing we want to do, we're going to calculate part A. And the way how we calculate part A, we first write the general formula for the electric field. So in this case, this electric field equals KQ over R squared, and it's away from Q. So in this case, they're just probes. And so for point A, we write the constant charge times the charge, and then over the radius, and it only has I direction. So, and since you can look at the graph position here, we only have X position, we don't have Y. So we're going to look for the I coordinate, not the J coordinates, which is why I indicated here A. And so we're going to write this, and then we get 4.3 times 10 to the 4 I newtons over coulomb. And that's just for part A. Now we're going to look for part B. If you notice part B, the vector lies not on the linear pathway. So we have to break into components. EX here and EY here as well. And so since I label my coordinates this direction, we assume that X goes in the negative position and Y goes opposite. I mean, it goes upward, which is positive direction. And so we also know that this angle here makes a perfect right triangle. So then we know that the angle measuring here is 45 degrees. And so in point B, we write our formula here. So EBX plus EBY equals a total vector formula, the summation of this. And so since we break it apart, we now write it in vector component form. So negative EB cosine 45I plus EB sine of 45 degrees. And so now we just also fire formula as well here, and then plus 9 to the plus I direction and plus J direction. So one thing I forgot about to write here was the sine of 45. So we know that sine of 45 is equal to radical 2 over 2. So now I can just plug in here times radical 2 over 2 I direction. And then same thing here, so be radical 2 over 2 J direction. And so after we calculate all that, we get a value of negative 1.5 times 10 to the 4 I plus I 0.5 times 10 to the 4 J. So what does this mean? This means that our probe is indicated in some direction here. So this is indicating the magnitude of this direction as well. This is just a clear indication of the magnitude. Now we're going to look for point C. And point C is basically the same process. The only thing that changes is just the position. So for point C, the only thing that changes is just the direction. And so if we look at the table here, it's going downward. So what we're gonna do, we're gonna break into components form. And so the way how we break it, so we just put EX and EY. So EX is negative direction, and EY is also negative direction. And so we label our graph. So we're gonna write here EC vector, and then ECX, and then plus EC, and then this one because they're magnitude Y. And the same thing, so we're going to have right negative EC cosine of 45 I direction plus, or in this case, since it's going downward, it's negative, minus EC sine of 45 degrees J direction. So since we break this on point and form, we're gonna draw this angle. So in this case, since it's opposite or adjacent, so EX is gonna be cosine and EY sine, just like we wrote here. And so another way we could do this too, we could factor out the negative 2y, so the radical 2 to be radical 2 over 2, negative EC I direction minus EC J direction. So radical 2 over 2, and then we know that this is just minus, so this is minus, so we could factor out the negative as well, and then we could create a K, so it would be 9 times 10 to the 9 units meter squared over coulomb squared, and then times 12 times 10 to the negative 9 coulombs, plus, since I factor out the negative here, same as well, so just because I ran out of space, I'm just going to write K times Q, which is 12 nanocoulombs, over R squared. So in this case, we're going to have negative 5 times 10 to the negative 2 meters, and then I direction here, and then J direction here, direction there, and then I'm going to write here negative 5.2 times 10 to negative 2, negative 5.0 times 10 to negative 2 meters. And so I should get negative 5.1, negative 1.5 times 10 to the 4 I direction, minus 1.5 times 10 to the 4 J direction. And all of these are in terms of newtons over coulombs. And so this makes sense because since this is just basically the opposite of the sharp charge, so we should get our same components that we got in the previous problem. And so since that is the case, that this should be the same as the B component, the C component.